Have you ever wondered how your computer can find one specific email out of thousands in a split second? Or how a giant spreadsheet gets sorted with just a click? Well, it all boils down to one single fundamental idea: sorting. So let's dive in and see exactly how computers take that messy, chaotic data and turn it into something organized and genuinely useful. You know, our whole digital world, from patient records in hospitals to every financial transaction we make, it runs on order. This ability to organize information is like the invisible engine that makes everything work, turning a complete jumble of data into something we can actually search, analyze, and make sense of. And getting our data in order isn't just about being neat, it's about pure, raw power. When data is organized, programs just run faster. It ensures our information is accurate and reliable. It lets systems grow and handle more data without completely falling apart. And, maybe most importantly, it makes it incredibly simple for us to spot patterns and trends. Okay, so before we can even start organizing anything, we need a place to hold all our data, right? That brings us to our very first building block, the basic container for information in the world of programming. And that container is called an array. Now, the easiest way to think about this is with a couple of analogies. A single-dimensional array, that's just a simple grocery list. One item, then the next, all in a single line. But a multidimensional array is more like a spreadsheet or even a bingo card with rows and columns. Perfect for when your data is a bit more complex. All right, so we've got our container, the array. Now we need an action. This next building block, it is the single most important fundamental move in so many of the classic sorting methods we're about to look at. And that action is swapping. It's as simple as it sounds. You take two items and you just switch their places. It seems almost too basic, but this one little move is the engine that drives the sorting machines we're about to build. It's the key that lets us rearrange a list from total chaos into perfect order. So now we've got our building blocks ready to go. We have arrays to hold the data and the swapping action to move it around. With just those two things, we can now construct three totally different sorting machines, and each one has its own unique logic for getting the job done. First step is bubble sort. Its strategy is really simple. It just steps through the list, looks at two items right next to each other, and swaps them if they're in the wrong order. It keeps doing this, and the larger values slowly bubble up to the end of the list, just like bubbles in water. Now, it's not the fastest method out there, not by a long shot, but its simplicity is perfect for when a list is already almost sorted. Let's actually watch it work. First step, it looks at the first pair, 5 and 1. Is 5 greater than 1? Yep, so they get swapped. Now it just scoots over to the next pair, 5 and 4. Again, 5 is bigger, so they switch places. You can already see the larger number, 5, starting its journey over to the right. And the same logic applies to the next pair, 5 and 2. A quick little comparison shows they're out of order, so another swap is made. Finally, it compares 5 and 8. Is 5 greater than 8? Nope, so no swap needed. And just like that, the first pass is done. And look what happened. The largest number, 8, has successfully bubbled up all the way to its final correct spot at the end. Pretty cool. Okay, let's move on to our next machine, selection sort. This one has a completely different strategy. Instead of just looking at its neighbors, it scans the entire unsorted part of the list to find the absolute smallest item, and then it swaps that item into the correct position. This method is fantastic when swapping items is actually a slow or expensive operation, because it makes the absolute minimum number of swaps necessary. So, let's see it in action. In its first pass, selection sort scans that whole list, 64, 25, 12, 22, and 11. It quickly identifies that 11 is the smallest value. Then it performs just one single swap, putting 11 right in the very first position, trading places with 64. And with that one swap, the first position is now perfectly sorted and basically locked in. We can see the sorted part of our array has started to grow from the left, and now the algorithm can completely ignore that first spot for the rest of the time. So for the second pass, it does the exact same thing, but only on the part that's left unsorted. It looks at 25, 12, 22, and 64, finds that 12 is the smallest, and swaps it with a 25. Now the first two elements are sorted and locked, and it just keeps going like that. Our final classic sorting machine is insertion sort, and this is probably the most relatable one of all. Honestly, if you've ever organized a hand of playing cards, you've basically performed insertion sort. That's exactly how it works. And because it builds the list one item at a time, it's super efficient for data that's arriving in a stream, like, say, news scores being added to a live leaderboard. Okay, here's how it starts. We assume the very first item, in this case the 5, is our sorted hand. It's a hand with one card, so it's sorted by default. Now we pick the next card from the unsorted pile, which is the 2. Now we ask, where does this 2 fit into our sorted hand? Well, it needs to go before the 5. So the algorithm just shifts the 5 over one spot to make room and inserts the 2. And just like that, our sorted hand is now 2-5. Let's do one more. We pick the next card, the 4. We look at our sorted hand, 2-5, and we find the right spot for it, right in between the 2 and the 5. We insert it, and our sorted hand gets bigger. It just repeats this over and over until the whole list is sorted. So we've seen how these algorithms work, and they all have their own little quirks and strengths. But why does it matter? Let's look at the real payoff by connecting these pretty abstract ideas to a very real, tangible problem. Have you ever needed to find the median value of something? You know, the exact middle point in a set of data? It's a huge deal in statistics. And notice step 1. It's not optional. You simply cannot find the median without first sorting the data using an algorithm just like one of the 3 we saw. And this is exactly why sorting is so incredibly powerful. Once a list is in order, finding the median is just easy. If you have an odd number of items, it's literally the one in the dead center. If it's an even number, you just average the 2 middle numbers. Sorting takes a potentially tricky problem and makes the calculation completely straightforward and accurate. You know, we've just looked at the foundational algorithms. Think of them as the Model Ts of sorting. They're brilliant for learning the concepts, but they are not what's powering our modern devices. And that leaves us with a really fascinating question. How in the world does your phone sort thousands of photos or contacts almost instantly? Well, the answer lies in much more advanced, way more efficient algorithms, all built on the very principles we explored today.